Today we will be simulating chance events. Okay, in this board game, there is a 2 out of 9 chance of drawing a card that gives a player a double turn. The remaining cards are single turn cards. A player wants to run a simulation to estimate the probability of drawing 2 double turn cards in a row, assuming the first card is replaced and the deck is shuffled afterwards. How can the player model the chance of drawing 2 double turn cards in a row? Design a simulation. So we have it's 2 out of 9. Okay, so if we have a spinner with 9 sections, okay, and we can label 2 of them with a D and the rest S's. Okay, this would be one way to simulate this type of event. Okay, so um, the if we spin the spinner, okay, and it lands on a D, we would record a D in our simulation. Okay, if it lands on an S, we would record an S. Okay, so this one, part B, does this and it creates their simulation and they run it through with 10 trial runs. It says, suppose the table shows the result of 10 trial runs. Okay, now the theoretical probability is 2 out of 9, right? Okay, that means in theory, if you uh, drew a card 9 times, twice you would get a D or a double turn card, and the rest of the time you would get a single turn card. But we know that when you actually start drawing cards, that may or may not be what happens, okay? So the experiment or the experimental probability might have a slightly different percent probability than our theoretical of 2/9, okay? So again, a D represents the double, S represents the single turn. All right, according to the results of the simulation, what is the experimental probability of drawing 2 double turn cards in a row? Okay, so if we look at this, we've got 2 single turns, 2 singles, a double and a single and a double, single, 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 double, single. Oh, here's our double, double, single, singles, singles. All right, so 1 out of our 10 trials gave us 2 doubles back to back. Okay, so this is 0.1 or 10% of the time. Okay, so according to our experiment, it would be 10%. Now, actually, 2/9 is 0.22 or 22%. Okay, so uh, theoretically, you'd get it 22%, but we only got it 10% of the time. Okay, so that's kind of the difference in that theoretical and experimental probability. Okay, let's take a look at another one here. This is similar. A pack of trading cards has a common holographic card and rare holographic cards. Um, there is a 1/8 chance that the holographic cards are rare. Okay, a collector wants to run a simulation to simulate or to estimate the probability of getting 2 rare holographic cards when opening packs of cards. Okay, when opening 2 packs of cards. How can a collector model the chance of getting 2 rare holographic cards? Okay, we can model this the exact same way they did the first one with our spinner. Okay, we can do a spinner with 8 sections, okay, where 1 out of the 8 is rare and the rest are common, okay, with the C's. All right, then let's take a look at our table here for the experiment. It says, according to the results of the simulation, what is the experimental probability of getting 2 rare holographic cards when opening 2 packs? Okay, so the first pack did not have any, it only had common. And the second pack did have a rare, but we only had 1. Okay, I don't see rare, rare, only 1 rare, 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 none, 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 none. Only one rare, none. So 0 out of our 10 gave us rare cards. Okay, so that is a 0% that is going to happen. Okay, here's number 3. You can try that one on your own. Okay, and number 4, there's one more you can give a shot on your own as well.